Thanks, everyone. So I'm also mostly like to share some philosophy, how we deal with the design infrastructure. How do we deal with the modulate interaction infrastructure with the environment? So for example, like we design pavement for performance. So primarily we design for the service load, like traffic load, but environment is also an important factor. So, for example, MEPDG, we not only consider the design traffic load over the design life, but the climate is an important factor in the whole process. So in terms of the influence of climate on the infrastructure wise, we can have the like a temperature, for example, humidity. All these have a lot of fluctuations. For instance, solar cycle, dry white cycles, solar radiation. All these things institute the influence of climate on the infrastructure. Then the thing become like the infrastructure always be a barrier of the environmental load, or they can coordinate with environment. So that's the general maybe issue we try to look into. So essentially, we try to define this also as a what's called a environmental responsive design. So for this case, for the pavement. So essentially, associated with a lot of environmental related pavement performance issues, like at high temperature, we typically have a lot more rotting in the pavement structure. And then like influence of the pavement for surrounding. So maybe also had some negative health impacts and also energy consumption needs associated with urban heat island effect. On the other metrics of the environmental impact is low temperature. So at the extreme low temperature, we can see a lot of crackings. So the current design, obviously, this infrastructure design, we are more like a bearing, like the infrastructure play a role as a bearing, to bear the environmental condition. So we design a road, in this case, infrastructure like this road, so passively suit what the environmental demand on them. So essentially that the consequence is, for example, if we asphalt road, which 94% of interstate highways built with asphalt, under a hot day, they can be very hot and contribute to the urban heat island effect. They can generate volatile gas for some smelling. And also because of the reduced viscosity, they cause larger rotting, which compromise performance. So essentially, because the fundamental reason is that when we design the material, like road and material, we only focus on mechanical performance as the primary design goal. So the consequence is that the design along this line lead to the infrastructure is a passive barrier of the environment, so they don't achieve maybe the potential benefits of modulate environment. So that's a what we try to propose, what's called the active infrastructure or adaptive infrastructure, which means they actually work with the environment, modulate the environment. So demonstration here is just so for example, like if use asphalt pavement as an example, like at a hot day, like when the road becomes very hot, maybe the material itself should be designed to deal with the heat. So maybe they should have higher solar reflectance, so that they actually work with the environment, modulate environment. So we don't solely rely on high performance material in the mechanical aspect to meet the performance needs. So that's some other questions. So essentially, we have a unitary performance goal or design philosophy right now. But if we can extend them to multiple functions, then they play a role, make the infrastructure to play a role to interact and modulate the environment, then we have a lot of more additional benefits that maybe has been ignored or has not been materialized with the current design philosophy. So as one example is we try, because we have been very interested in how to make the road manage the thermal boundary, because at high temperature end, the high temperature cause a lot of environmental issue, performance issue. On the other side, low temperature also cause a lot of performance issue. So in the biology system, they have very good strategy to cope with the changing environment. Like this is like a Cameroon, these are living in the desert. So essentially at a very hot temperature condition, the skin color will change so that like they become more reflective. So they can help the body to cool down the temperature. Essentially, it is about from this kind of biology, thermal modulation, we try to come up with a material, like a pavement material, so that can deal with extreme cold environment, deal with extreme hot environment. So in this aspect, we're looking to properties beyond like a mechanical property. So this is like a solar reflectance, like a modulation. So essentially, this is a what's called a thermochromic material that will be activated by temperature threshold. Like in this case, when the temperature raises, the color become lighter. Essentially, they become more reflective. And then on the other side, when the temperature decreases, they become darker, which means they become more solar absorptive. So essentially, they help to deal with both bandwidth, extreme high temperature, extreme low temperature. So what we try to explore. So essentially, another maybe unique feature is this type of material is we see some like a change in the optical, like visible range, but we also, this material itself also play a big role in the infrared range, which means because around 50% of solar radiation is from infrared. So if we have good way to modulate infrared, then we'll have a lot of potential benefit, which from the user aspect, the driver will not see a big difference from the road appearance. So essentially, with this idea, then we look into a lot of intensive study from material design, from the asphalt binder design to the asphalt concrete design, and then see what are the potential benefits if we leverage this active material into the pavement design. So because we're looking at the two different dimensions of pavement material design, so we then need to look into beyond mechanical performance alone. So for example, in this case, from the thermal, optical, mechanical, and also if we upscale them for plant production, we also study the thermal stability issue. So make sure they are producible compatible with the current production procedure. So essentially, these some examples like from the thermochromic powder, they have their reflectance is significantly affected by first they are very effective in the infrared range. The other is they are modulated by the temperature. And if we introduce into the asphalt binder, then we did see some response. So a lot of like compared with the pure asphalt material, which is at the baseline, essentially incorporate this thermochromic material into asphalt binder. They modulate the solar reflectance, but mostly in the infrared range. So that's the performance benefit we try to look into. So essentially, and then in order for the material to be industrially accepted, they still need to be adapted to the industry specification. So for example, this is a comprehensive like silver pay asphalt binders grading testing like a schema. So essentially, a range of testing need to be satisfied in the material for the material to be accepted by the industry, like a practice standard. So essentially, what we did was we had a sensitivity study, introduce the material into different concentration to the regular asphalt, and see what kind. So beyond the current mechanical performance acceptance criteria, so what's the solar modulation performance we can like piggyback on. So this is just we did a range of testing from binder aspect, from hot mix asphalt concrete aspect. So there are some examples of this testing process, and then from the asphalt concrete itself, we also see compared with baseline pure asphalt concrete made with regular asphalt binder. For asphalt concrete made with solar adaptive asphalt, we also see big difference in the solar reflectance. So essentially, we did some different type of testing and the laboratory and emulated field condition. It's just an example, like one comparison. So from the visual appearance, like the different type of asphalt concrete, they look the same essentially. So which is a benefit, like a driver will not see a difference when they operate on the road. And we expose to different environment conditions to see. So So general observation. So this is like a Cleveland. Typically don't have a extremely hot weather or cold weather. So like in the hot climate condition, typically solar modulated asphalt concrete typically have lower temperature compared with regular asphalt concrete. And then in the cold condition, like a low temperature condition, like evening, mostly the solar modulated asphalt concrete have higher temperature. So which is also another aspect, like potentially say the benefit. So some based on some European country studies, for example, reducing the maximum temperature on the pavement surface can lead to some performance benefits for life extension. The observation is a 1 degree reduction in the surface temperature. The highest surface temperature lead to 1 year extension of performance for the rotting performance. So essentially, based on our observations, we essentially see more effective reduction of surface temperature by 5 degrees over the regular season. So potentially can map to 5-year extension to meet the rotting performance criteria. On the other side, because the low temperature bandwise, like temperature is higher, so we don't have any issue with low temperature cracking, deteriorate low temperature cracking issue. So that's just like a benefit, like the material can be adaptive based on the environmental condition. So we're also looking into if we mix the material, make it compatible for the production process. Because we don't want to add this material, the regular asphalt produced with the temperature condition for hot mix asphalt or warm mix asphalt. For production wise, when we add this new material into the binder, we don't want to see a difference in the thermal stability, this kind of issue. So essentially, just from the subjection to the production condition, for example, for the high temperature, maybe subject to a few hours, we see if the solar reflectance has been affected by the production process. So that they maintain effective after the subject to the production thermal condition. So that's also critical for the field implementation. So essentially, the observation is for most solar adaptive asphalt binder, after they subject to the thermal treatment in the asphalt plant, they still maintain the effectiveness in terms of the modulating solar reflectance. Except some exception case, some like a compromise because maybe there's some material stability issue. So essentially, from this multifunctional characterization, using what we general observations, they have an influence introduced of solar adaptive components is asphalt binder asphalt concrete design, leads to some change of different multifunctional property from thermal property, optical properties, mechanical properties, and also from the thermal performance aspect can help to reduce the high temperature and increase the low temperature. And also from the production side, it's comparable with the current production procedure without being compromised. So that's maybe my quick overview about the idea we tried to explore. So I also want to thank the funding support from the center and also National Science Foundation, and also my group members who contributed to the research. Okay, thank you.
Thanks, Bill. And any questions for Bill? Thanks, Bill. Interesting session. One question is, with this type of additive, have you evaluated the risk of motion damage?
Yeah, we saw actually, yes. Just although we have not primarily focused on this part. So for the accelerated pavement analyzer testing, the testing protocol we conducted was under the water. Like a high humidity condition, water condition. So the observation is this material, because maybe they have some polymer component. So actually they have achieved a little bit higher rotting resistance compared with the regular asphalt. Yeah. Thank you.
Question over here. Just looking at this, because taking an angle, increasing the reflecting asphalt, sometimes it's dangerous for life.
You mean increase the risk?
If you're driving, there's about 100% get dark.
Oh,
Is there an impact? When you think of cleaning?
no, yeah, that's a very excellent question. Actually, that's what issue we considered. As some of the data show, mostly the solar modulation happens in the infrared range. And the concentration introduced into the actual band is very small. So visually, some photos show a different contrast sample. They look the same from naked eye. Yeah.
Any other questions? So I have one quick question. Great presentation, very interesting. You shared a little bit about the super pave specification and trying to meet those existing specifications to satisfy the DOTs. I know when we started adding polymer modifier to asphalt binder, a lot of states had to kind of change the specification because the current specification wasn't very good at identifying the polymer. So they started to use the MSCR test instead to identify, the advantage that polymer provided. Do you see maybe a need that the binder specification has some revisions in the coming years because of these new type of additives?
Yeah, that's a very interesting question. So for our case, because I would say definitely there's some limitation with the current super pave specification because they they primarily only focus on mechanical performance aspect. So from our observation, we say, like you mentioned, because this material we use has a polymer base. So this is in one side, the actually is a polymer modifier, makes the material matrix to be stiffer. The other side is they actually can modulate the temperature range. So essentially, from the performance aspect, they have two different performance. Well, with the current specification, we only we can only leverage utilize one aspect performance. And then because for DOT, for them to accept the material, they have they must certify their design code. So that's why we try to characterize the material to meet the DOT specification. But then, like you mentioned, there may be other dimension of the performance property that has not been completely accounted for.
Great, thanks. Okay. And there's one question online. It says, which of HMA or WMA do you think work better regarding drainability of asphalt?
Which aspect, sorry?
It says which of HMA or WMA do you think works better regarding drainability of asphalt?
Drainability.
Yes, drainability. Yeah, maybe they
drainage.
Drainage. How to mix asphalt or one mix asphalt, which what the better was drainage.
I guess that's the question.
Drainage. You mean what?
Drainage of water.
Drainage of water. Yeah.
That could be a question.
Yeah.
Yeah, it certainly relates to that.
Okay, because we frankly we didn't focus on the hydraulic conductivity as the primary focus. Yeah.
Yeah. Well, I can speak a little to that, I guess, because we looked at that. Generally, for the drainage, I mean, if you want to use porous asphalt, you need a very polymer modified, very good binder. So it's going to be very difficult to use a WMA. In that case, I mean, WMA usually has to be pretty soft. Porous asphalt, you need something very stiff because otherwise it would be susceptible to running and other durability issues. So I would recommend using HMA for probably only we are trying to achieve drainage through the pavement. Okay, well with that, I think we'll wrap up. Thank you so much, Bill.
Thank you.
And,